In this video, we're going to introduce Section 7, Substitution and Elimination Reactions of Alkyl Halides, which is covered in Chapter 7 of our text. And specifically, we'll cover 7.1, Alkyl Halides and Alkenes. So in this section, we're going to look at substitution and elimination reactions in a significant amount of detail. And substitution reactions of alkyl halides can lead to the formation of various functional groups, various functional families. As well, elimination reactions of alkyl halides, they're the primary method of forming alkenes. And so that's what we're going to look at over the course of the next series of videos. Now, before we look at substitution and elimination reactions, I'd like to discuss how we name alkyl halides and alkenes. Now, the term alkyl halide itself is a common name associated with this functional family of compounds. The IUPAC systematic name would refer to alkyl halides as haloalkanes. That is, the halogen in these compounds is considered a substituent. The common name treats it a little bit differently. It often will refer to the alkyl group as a substituent connected to a halogen, and we would term that halogen a particular halide. So when we're naming alkyl halides or haloalkanes, the halogens are simply treated as substituents. So you can see in this example that we have a 3-carbon chain that will give us prop. It's an alkane, ANE, so propane. And then when we number the parent chain, we see in this example that this chlorine atom is attached to carbon 2. So the locant for this particular compound, or for this particular substituent within the compound, is 2. And the substituent, the chlorine atom, is referred to as a chloro. So fluorine becomes fluoro, chlorine, chloro. So you drop the INE in those particular halogens and you add the letter O. Be careful with the spelling of fluoro. It's not flower O, so we don't spell it F-L-O-U-R-O. It's F-L-U-O-R-O, so fluoro. All right, so in this example, this first example, it's a 2-chloropropane. In this second example, we have a 5-carbon chain, so that gives us pentane. We have branching at carbon 2. We both have a methyl group located here, as well as a bromine group. And so we have a bromo substituent and a methyl substituent. And so we would alphabetize the substituents. The B in bromo precedes the M in methyl. So it's a 2-bromo, 2-methyl pentane. And notice again that we're using hyphens between numbers and letters in each of these cases. Now let's look at one example of a haloalkane. In this example, let's count the longest continuous chain of carbons. So we have 1, 2, 3, 4, 5, 6. We could go 1, 2, 3, 4, 5, 6, or as well down this route. It's all the same. We're going to end up with hex as our longest continuous chain. And so when we're writing out our name, hex ane, because it's an alkane. And now we want to identify any substituents attached to that parent. Now, in this example, we have if we're numbering our parent chain, we have the fluorine atom as a fluoro group. So the fluoro group is at position 2 if we were numbered from this direction. If we started from this end, these methyl groups would appear also at position 2. And so what gives precedence is the fact that you have two methyl groups off this particular carbon versus one substituent, the fluoro, off this. So your set of locants, we have 2, 3, 4, 5. So we have a 2, 2, 5 as opposed to a 2, 5, 5. And a 2, 2, 5 is a lower set of locants, and so it would take precedence. So in our numbering of the parent chain, this will be 1, 2, 3, 4, 5, 6. And so we can identify our substituents. We have a 2,2-dimethyl as a part of our name, as well as the fluoro. Now recall that the D in di, the multiplier prefix in dimethyl, it is not alphabetically relevant unless it's a part of a complex substituent. So we have a 2,2-dimethyl. We have a 5-fluoro. And it's the M in dimethyl and the F in fluoro. So if we bring everything together, we have a 5-fluoro, F-L-U-O-R-O, hyphen 2, 2, hyphen dimethyl, hexane. And so that would be the name that we give to this particular structure. Now there is one thing missing. You may have recognized that we have drawn the fluorosubstituent on a three-dimensional bond. So we have a solid wedge associated with the carbon-fluorine bond. So the first thing to do is to check as to whether that carbon to which the fluorine substituent is attached, is it a chirality center? So if we take a look, do we have 4 different substituents attached to this particular carbon? We do. We have the fluoro group, this methyl group, the remainder of the molecule, and there's a hydrogen not being shown. Now that hydrogen, if you wish, you could draw it in, but be careful where you do draw it in. It's important to never split the three-dimensional bonds. And what I mean by that, I'll just show it down in the corner here, is that when we draw a tetrahedral, the 2 bonds in the plane are always, in a sense, neighboring one another when we draw our structure, whereas the three-dimensional bonds are also always neighboring one another. This is a proper tetrahedral. What's not a proper tetrahedral is the following, if we were to draw this type of structure. This is in fact not a tetrahedral, but another type of geometry known as square planar. And so you never want to split, meaning the three-dimensional bonds, solid wedge or dash wedge, should be neighboring one another and not split on either side of the bonds that are in the plane drawn by the straight line. So this is a tetrahedral, this is not. So be cautious of that when you're drawing your chirality centers or three-dimensional structures. Now in this example, I can place the hydrogen here or I could place it here, but in either case, it's going to give you the same result because again, when we assign the stereochemistry, the configuration of that chirality center, the lowest priority group, so long as that is in behind the plane, which in this case, the hydrogen is the lowest priority group. If it's in behind the plane, if I draw it here or here, we get the same perspective. All right, so as a part of this question, let's rank the substituents attached to the chirality center. So fluorine does have a higher atomic number than carbon, second row element, but it is higher. Hydrogen will be 4. And so now we have to look at the other groups attached. To this group, we have our methyl, we have a carbon directly attached here, also a carbon. So we could write that out. So we have carbon versus carbon. Carbon 6 has to that carbon 3 hydrogens, so I can put those here. And carbon 4, to it, there's 2 hydrogens, but there's also another carbon at position 3. So we have carbon, hydrogen, hydrogen. So when we compare the first atom in our list, carbon versus hydrogen, carbon is going to be our highest priority, or our highest atomic number. So that would make this group here our second highest priority group. So we'll make this 2, and we'll make this 3. So now we're looking down this carbon-hydrogen bond, we're looking down in this direction, and we'll trace the direction, starting from the highest priority group, we'll trace the pattern, if you will, that we make as we go from 1 to 2 to 3. And you can see that what I'm tracing is the clockwise direction, going to the right, and so this would be the R configuration. And so we can complete our name by putting in brackets in front of the name R, so open bracket R, close bracket, hyphen, 5 hyphen fluoro hyphen 2,2 hyphen dimethylhexane. So that's how we would name this particular haloalkane. And again, the last thing we always want to check when naming organic structures is any kind of stereochemical descriptors that may be missing. So we're looking for cis and trans, R and S, and when we look at alkanes, we'll introduce our third and final stereo descriptor, the EZ system. Now there's a couple other points I want to mention about alkyl halides before we move on to the naming of alkenes. The first being is that when we discuss the reaction mechanisms for the alkyl halides, we will often refer to the carbons involved in those mechanisms using Greek letters. And so, as you can see in this example, the alpha carbon will be the carbon that's directly connected to the halogen, whereas the beta carbon will be the carbon that's directly neighboring the alpha carbon. So as we've seen for carbocations, we can also classify alkyl halides based on the number of alkyl groups attached to the alpha carbon. So alkyl halides can be classified as primary, secondary, or tertiary based on the number of groups. And so you can see for the primary alkyl halide, there is 1 alkyl group attached to the alpha carbon, and the remaining bonds of that carbon are to hydrogen. In the secondary alkyl halide, we see there are 2 alkyl groups that are attached to the alpha carbon. In tertiary, there are 3. So we'll use this classification or way of categorizing alkyl halides because we'll observe that the reactivity of primary, secondary, and tertiary alkyl halides, they are similar in some ways, but different in other aspects. And so those differences can be observed quite frequently for different categories. And so we'll group the primary alkyl halides as having similar reaction mechanisms as other primary alkyl halides, but different from the reactivity that we observe for secondary or tertiary alkyl halides. So we'll use these terminology frequently when discussing the mechanisms of alkyl halides in general. Okay, so let's look at the naming of alkenes. So we saw previously for alkanes that we would use the suffix ane to represent that the parent chain in this particular molecule was a, if you will, saturated hydrocarbon, meaning there was sp3 hybridized carbons in the parent completely, and everything else was hydrogens, or in this case now, possibly halogens. For an alkene, there's going to be some unsaturation. So there's going to be sp2 hybridized carbons involved in the alkene. So again, The alkene functional group involves a pi bond within our system. So we have a double bond where we have a sigma and a pi between two carbons. And so the suffix that's used for alkenes is ENE. Now, when we choose the parent of an alkene, we have to ensure that we're choosing the longest continuous chain of carbons that also includes both carbons of that pi system. So both carbons of the pi bond need to be included in the parent chain for you to refer to that structure as belonging to the alkene family. So you can see in this example, if we were to name this particular compound, we would identify the longest continuous chain as having 8, and so that gives us oct, and it's fully saturated. There's no double or triple bonds, and so this would be ANE, representing the alkane family. When we look at this similar example, where now we have a pi system or a pi bond, a double bond, what appears to be possibly a substituent, but in fact it's not. It's a part of the parent. So even though there's a longer chain of carbons in this direction, this part of the molecule does not contain the double bond. And so we need to refer to this as the alkene, and so we need to include this as a part of our parent chain. Now we have two options. We could go 1, 2, 3, 4, 5, 6, so it could be a 6-carbon system, or as shown in red, 1, 2, 3, 4, 5, 6, 7. That will be the longest continuous chain that includes the pi system, the double bond. And so the proper IUPAC systematic name would be hept, indicating that there's 7 carbons in the parent chain, and ENE would be used to indicate that it is the alkene family to which the structure belongs. Now we'll see in the upcoming slides that we also have to number the location of this double bond. This would be a 1-heptene because the first carbon of the double bond is carbon 1 if we were to number that chain. So we'll discuss that in just a moment. So here's the example of that. So when we're numbering the parent chain of an alkene, the pi bond receives the lowest number possible, despite the presence of alkyl substituents or halogens. We always have to give the lowest possible locant to the alkene. So you can see in this example, we could number this in 2 ways. We could have the first carbon of the double bond being at position 2, or the first carbon of the double bond being at position 5. 2 being lower than 5, we're going to refer to this as a 2-ene or a 2-hex or heptene, and we'll see that on the next slide. So once you've identified the position of the double bond, then the locants with respect to all the other substituents will be placed in accordance to that numbering. And so you can see in this example, we have, as a part of our name, our longest continuous chain is 7. We have 3 methyl substituents, 2 at branching off position 5, and 1 off carbon 6. And so this will be a 5,5,6 trimethyl. And there's 2 ways in which we can identify the alkene. You can see that we have to identify the location of the double bond, because this could be between 3 and 4, or between 1 and 2. And so that would give different isomers, different constitutional isomers. So we have to use a name that's unambiguous, that's specific to every structure. And so we have to identify the location of the double bond in this example. And so this will be a 2-heptene because the first carbon, the lowest locant associated with the double bond, is 2, not 3. So it's a 2-heptene. You can see there's 2 ways we can do it. We can place the locant in front of the term heptene, or we can use the parent, hept, and then before we add the suffix, we include the locant 2. Both names are acceptable, but admittedly, my preference is towards the latter because, as you'll see, going forward that occasionally there'll be two functional groups that you have to include in the latter part of that name. And so it makes it a little bit easier if the locant is found within or separating the parent from the suffix. So we'll see that a little bit later. Now my question to you is, what is missing from this name? And I hope you'll recall from earlier discussions that we have isomerism around carbons 2 and 3. So we could refer to this as either a cis or a trans because we are looking at a di-substituted alkene. So you'll recall from section 5 when we were talking about stereoisomerism. Yes, we have ways to identify configurations using the RS system, but in our diastereomer example, we can have cis and trans associated with planes, and a plane meaning either a ring system or in this case, the sp2 hybridized plane associated with the alkene. And so you can see in this example, because substituents 1 and what's starting at carbon 4, so this methyl group and the remainder of this molecule, as they are across the double bond, we refer to this as a trans. And so what's missing from this name is trans, and so we would write that out, trans hyphen, and then the rest of the name would be associated with that. So that's again reminded here that we have stereo descriptors cis and trans, and these are used to indicate the relative arrangement of those groups. Typically, we use cis and trans for di-substituted alkenes and for cycloalkanes, assigning substituents on either side of the ring. But in this example, you can see we're using the cis and trans to represent the placement of these two methyl groups. And again, the easiest way for me to remind myself of cis and trans is that when I take and trace from one substituent to the other, if I don't have to cross the double bond, they're on the same side, if you will, of the double bond, and that gives us our cis. Whereas if I draw a line, most direct path between these two groups, and I need to cross that double bond, trans, meaning across, is used in that example. Now, when we have more than two substituents surrounding an sp2 hybridized carbon-carbon system, so a double bond, how do we treat that? We can't use the stereo descriptor cis and trans so easily. There are some older rules that can be used to describe tri and tetrasubstituted systems using the cis-trans stereo descriptor nomenclature, but we're not going to go into that level of detail. If you're interested, I can definitely discuss it with you in a Zoom call. But we're going to show you a simplified system very similar to the RS system, and that's referred to as the EZ system. So in this example, you can see that we have very similar molecules, but the placement, if you will, of the amino group, NH2 as a substituent is referred to as amino. I'll write that out. The amino group, you can see, is either neighboring through space, cis, if you will, to the fluorine atom, so the fluoro group, or the amino group is across from this fluoro group. But we can't use cis and trans in this particular example because cis to what would be the question. This amino group is cis to this ethyl group, but it's trans to the fluoro group. So we need a more rigorous system to deal with these particular compounds or naming of them. So the system that we use is referred to as the EZ system. And so similar to assigning the configuration for a chirality center or the groups attached to a chirality center, we're going to assign priority to the groups attached to the carbons of the double bond. So if the higher priority groups are on the same side of the double bond, the configuration that we use the letter Z, and Z and E are based on German words. So the letter Z is for the German word zusammen, meaning together. But if the higher priority groups are on the opposite side, the configuration is designated with the letter E for the German word entgegen, meaning opposite. Now, a mnemonic or a saying that I commonly use to describe this, and no discredit to Deutschland or German language, but I was taught by a German professor organic chem. And when he introduced the EZ system and zusammen and entgegen, you know, we all kind of looked in bewilderment because most of us in the class had no experience with the German language. But he said an easy way to remember this is that the Z is when the groups are on the same side, and he threw a little bit of a funny twist to it. He referred to it as the Z-same side. So he kind of was making fun of his own dialect, but as a way of reminding us that Z was for groups on the same side. So Z-same side, I still use it today. I'm teaching it this way just because Professor Schmidt taught it me that way, and it stuck. So in this example, you can see that the two higher priority groups, and again, priority is based on atomic number. So we're using the same system that we use for RS. So we're comparing, when we're assigning priority, we're comparing the first atom directly attached to this carbon and the first atom attached on the other side. So when you're comparing priority, you're looking at each carbon of the double bond first, but you're comparing groups attached to the same carbon, and you have to do that twice. So the first carbon here, let's call it, we have a carbon versus a fluorine atom. The fluorine atom is higher in priority, and so it's going to be our highest priority group. Now we look to the other carbon of the double bond. We're comparing nitrogen with hydrogen, and nitrogen has a higher atomic number than hydrogen, so therefore it is also the highest priority group attached to that particular carbon of the double bond. Now, because these two groups are on the same side of the double bond, we're going to refer to this as the Z. So this is the Z configuration for this tri-substituted alkene. We're not counting the hydrogen, but you can see that there are this ethyl group, the fluoro group, and the amino group. So this tri-substituted alkene, this would be the Z system, the Z configuration, Z isomer. So if we go back here, this would be our Z. And again, similar to the RS, we put Z in brackets and then hyphenate it in front of the rest of the name. Whereas in this example, this would be the E, entgegen, meaning opposite, because the highest priority groups, the fluorine atom and the amino group, are on opposite sides of the double bond. So they're across, we give that E for entgegen. So let's look at an example where we name an alkene as well as use the EZ system. So in this example, we're going to start by counting the longest continuous chain of carbons that includes the alkene double bond. And so if we count that through, we have 1, 2, 3, 4, 5, 6. So hex will be our parent. Ene will represent the suffix for alkenes, and so we will have hex ene. Now when we're numbering our parent chain, again, we'll use the same rules. We want to give the lowest possible locant to the double bond. So 1, 2, 3 from this side, or 1, 2, 3. So 3 in either case. So this will be a hex 3-ene. Just write that out again. That's my preference. You could also refer to this as a 3-hexene. So either is acceptable. Okay, so now we look to our substituents. We have a bromo substituent. I hope you could see that. And iodine as a substituent. This would be the iodo substituent. So we have a bromo, iodo. And we could refer to this as a 3-bromo or a 3-iodo. And then the other substituent would be locant 4. And when that situation arises, where you could potentially refer to this as a 3-bromo, 4-iodo, or a 4-bromo, 3-iodo, you always place the substituents into your name alphabetically. If the locants can be swapped interchangeably and give you the same relative positioning, then in that situation, you would always put the lowest locant first. Okay, I don't know if we've seen an example like this yet in class or in the assignment, but that's how we deal with it. So let's look at that. So bromo, it's going to be the B in bromo, and iodo, it's going to be the I in iodo. Now, like I just said, we've identified our chain, call this 1, 2, 3, 4, 5, and 6. Yes, you could go the opposite direction, but now we have substituents off carbon 3 from either direction. But the reason why I've numbered it this way is that the B in bromo precedes the I in iodo. So a 3, 4 is going to be preferred over 4, 3 in our name. So we're going to give bromo 3 and iodo 4. So let's put that all together. So again, in this case, the locants are going to follow the alphabetical order when you have those two possibilities. So we have the 3 bromo hyphen 4 hyphen iodo, no spaces, hex hyphen 3 ene. Okay, so that's the majority of the name. The last thing to do when looking at your structures is look for any stereo descriptors. And so we're going to use the EZ system to identify the relative placement, positioning of the two highest priority groups around the double bond. So this is a tetrasubstituted alkene because on each carbon there are two substituents. There's this ethyl group in iodo. On this carbon there's a bromo and yet another ethyl group. And so I think you'll be able to see this relatively clearly that because it's based on atomic number, we're going to give the bromine and the iodo, the bromo and the iodo, highest priority because bromine has a higher atomic number than carbon and iodine has a higher atomic number than this carbon. So again, when you're assigning priority, you look to each carbon first. Okay, so we look to this carbon and we look at the groups attached to it. And if your first comparison, let's say it's 2 carbon atoms, you can't decide, then you go to what's attached to that, similar to what we saw for assigning R and S. So in this situation, it's relatively straightforward because it pops that the bromine and iodine atoms have much higher atomic numbers than carbon. So that's pretty straightforward. So once you assign priority to each of the two groups on each carbon of the double bond, then you look to whether or not those two groups are on the same side of the double bond. And then when we're talking about the side, we're kind of splitting the molecule through the 2 carbons of the sp3 hybridized centers, or through those sp3 hybridized centers. So this bromine atom, this iodine atom, if we take our pen and we're going to cross that double bond. And so this would give us the E. Okay, so it's a E, 3 bromo, 4 iodo, hex 3 ene. And if we want to draw the Z configuration, the Z isomer for this particular structure, we would redraw it with two of the groups would have to be exchanged. But we can't do that with a pi system. We'd have to do some chemistry to break that pi or weaken that pi system in order for that to happen, because we don't have free rotation around the double bond. So the last thing I want to discuss in this video is the degree of substitution for alkenes. And we've somewhat already discussed this by terming these alkanes as being di, tri, and tetra. But I want to go into a little bit more detail about what that actually means with respect to the stability of those alkenes. So we can see in this example that a monosubstituted alkene has a single group attached to either of the carbons of that double bond. So you're counting the number of substituents to both carbons in total. So in this example, we see there's 2 substituents attached to this pi system. Here, 3 and 4. And so we'll use these terms, mono, di, tri-substituted, tetra-substituted, to refer to the number of groups that are attached to the carbons of that double bond. Now, in general, the cis alkene is less stable than the trans alkene. And this has to do primarily with steric strain. And so the cis alkene is considered less stable than the trans. So the trans alkene is often formed in greater amounts than the cis alkene. And how do we know that cis and trans have this difference in energy? Well, similar to what we saw for when we looked at the stability of cycloalkanes, we'll combust these molecules. We'll burn them up and determine and measure how much energy is released during that combustion process. And so what's been observed is that there's about a 4 kilojoule per mole difference in energy associated with the cis and the trans. So the trans being 4 kilojoules per mole more stable or lower in energy than the corresponding cis isomer. And so that's how we determine it experimentally. We carry out these heats of combustion type measurements. The number of substituents has an important role in the relative stability of the alkene. And we use the same terminology that we've used previously with the stability of carbocations. There's a hyperconjugative effect that can occur by having more substituents surrounding that pi system. So as a result, the tetra-substituted system is more stable than the tri-substituted system than the di or the mono-substituted system. So in these examples, it's not a steric effect that's giving rise to stability. It's an electronic effect, specifically the hyperconjugation. So specifically, alkyl groups, these are electron donating via hyperconjugation. So these electrons in the neighboring covalent bonds of those alkyl groups, they can donate electron density into the sp2 hybridized carbon atoms of the pi bond. So as a result of that delocalization of electron density from neighboring covalent bonds into the pi system, this provides a stabilizing effect. And so again, we'll see this play out when we look at the regioselectivity of elimination reactions, which are used to form alkenes from alkyl halides. And we'll see that the predominant alkene that's formed under certain circumstances will be the more highly substituted alkene. So this is a bit of a lengthy video, but if you have any questions about nomenclature with respect to haloalkanes or alkenes, specifically the EZ system, or if you have any questions about some of the other vocabulary that we use or a discussion on stability with respect to alkenes, send me an email. We can meet via Zoom, or you can ask a question in our forum. Thank you.